you, Dr. Rajesh, for a kind introduction. And also I thank for inviting me to deliver a lecture in this e-seminar series. Let me present.
Yeah, you can share your screen. Yes.
Is it okay?
Yes, your screen is visible now. Yeah.
Okay. Thank you. I am talking today about distance spectra and distance energy of graphs. First of all, I will talk about some definitions and preliminaries, and then about the distance energy, and then our results we got, and some references. The distance matrix of a connected graph G of order n is an n by n matrix with entries dij, where dij is the distance between the vertices vi and vj. Here is a graph and the corresponding distance matrix is here. The distance between V3 and V4 is 2. So the entry V3, V4 is 2. Since we consider only simple graphs, the diagonal entries will be zeros. So if two vertices are adjacent, then the corresponding entry will be 1. So we can construct a distance matrix like this. And since we consider only undirected graphs, the matrix will be real and symmetric, and the diagonal entries will be zeros. Since distance matrices are symmetric matrices, the distance eigenvalues will be real. The eigenvalues of the distance matrix are called the distance eigenvalues. The distance eigenvalues, the collection of distance eigenvalues are called distance spectrum. And the largest distance eigenvalue is called distance spectral radius and is denoted by rho d of g. We denote distance matrix by d of g. This is a graph with integral distance spectrum. Integral spectrum means the distance spectrum consists of integers only. This is an example. The distance eigenvalues are 7, 0, 0, -2, -2, and -3. Next is a transmission regular graph. A transmission is denoted by TR of V for a vertex V in G, and the transmission of vertex V is the sum of the distances of all vertices from V. That is summation d of uv, distance from V to all other vertices. Sum of such distances is the transmission of V. A graph is said to be K transmission regular if transmission of V is a constant K for all vertex V in the vertex set of G. If the transmission of all the vertices is a constant, then the constant K, then K transmission regular graph. A K transmission regular graph in the case of distance matrix is exactly the same as regular graphs in the case of adjacency matrices. We know that in the case of regular graphs, every row sum will be a constant, and hence the spectral radius of an adjacency matrix of a graph is that row sum a constant. So we can have the spectral radius of a graph by finding the constant row sum in the case of regular graphs. Like that, if a graph is K transmission regular, the sum of the entries of each row will be a constant. then that constant will be the distance spectral radius. And if we consider a k transmission regular graph, that spectral radius will be k. Kn is an example for a transmission regular graph. In the case of Kn, the value of k is n minus 1. Since all the entries are 1 except diagonal entries, the sum will be n minus 1, row sum. When we consider Cn and Kmm, Cn is the cycle graph of order n and Kmm is the complete bipartite graph where m and n are same. These graphs are regular graphs and these graphs are transmission regular also. So there are regular graphs which are transmission regular. Also there exist non-regular graphs which are transmission regular. This is an example. This is a transmission regular graph but not degree regular. The vertex V2 have degree 3 but the vertex V1 has degree 4, but we can find the distance matrix and find the row sum and we can see that it is a transmission regular graph. Now we consider a strongly regular graph. A strongly regular graph is a regular graph, a k-regular graph, and it is said to be strongly regular if there exist two integers, p and q, such that any two adjacent vertices have p common neighbors and any two non-adjacent vertices have q common neighbors. That is, the number of common neighbors to adjacent vertices is a constant, that is p, and number of common neighbors to non-adjacent vertices is q, that is a constant. Then we say that the graph G is NKPQ strongly regular. NKPQ strongly regular graph. And the result is that any strongly regular graphs have exactly 3 distance eigenvalues. This is the same result as in the case of adjacency matrices. And strongly regular graphs are transmission regular graphs also. This is an example for a strongly regular graph. This is a well-known Peterson graph. It have distance eigenvalues -3 with multiplicity 5 and 0 with multiplicity 4. 15 with multiplicity 1, and 15 is the spectral radius, and the spectral radius is of course a simple eigenvalue. This is another example for a strongly regular graph with 16 vertices. This is the Srikhande graph and it also consists of 3 distinct eigenvalues, and the eigenvalues are -4 with multiplicity 6, 0 with multiplicity 9 and 24 with the spectral radius with multiplicity 1. This is the well-known Perron-Frobenius theorem. The Perron-Frobenius theorem gives us many properties of the spectral radius of a matrix A. If we consider an irreducible matrix, non-negative matrix n by n, then the spectral radius rho of A is a positive real number and is an eigenvalue of the matrix A called the Perron-Frobenius eigenvalue. So the spectral radius will be a positive real number and that spectral radius is called the Perron-Frobenius eigenvalue. And the Perron-Frobenius eigenvalue will be simple and it is denoted by rho of A and will be simple, that is of multiplicity 1. If A has an eigenvector corresponding to the eigenvalue rho of A, there exists an eigenvector corresponding to rho of A such that all its entries are positive. There exists an eigenvector corresponding to rho of A with all entries positive. This is the unique property for spectral radius, the Perron-Frobenius eigenvalue. No other eigenvalue have the property that it has an eigenvector with all the entries positive. It is the special quality of the spectral radius, the Perron-Frobenius eigenvalue. And case of trees, a very surprising result by Graham and Pollock is that the determinant of the distance matrix of a tree is equal to -1 raised to n minus 1 into n minus 1 raised to 2n minus 2. The surprise is that for any tree of order n, the determinant is the same because the determinant depends only on the order n. So, for any tree of order n, the determinant of that tree will be the same if we consider the distance matrix. And Graham and Lowas proved that it is possible to compute the inverse of the distance matrix of a tree in terms of degrees and entries of the adjacency matrix. Next is the graphs with unique positive eigenvalues. In the case of distance energy, unique positive eigenvalued graphs have much advantage to study the distance energy. We have some examples for graphs with unique positive distance eigenvalues. Graham and Pollock showed that all the trees have unique positive distance eigenvalue. And 1994, Coulon and Spectra characterized the distance regular graphs with unique positive distance eigenvalue. In 2005, Bipartite, Kirkland and Newman proved that unicyclic graphs also have unique positive distance eigenvalue and many other graphs. Now we come to co-spectral graphs. Co-spectral graphs means two non-isomorphic graphs with same spectrum. They are called co-spectral graphs. In the case of distance spectrum, if two non-isomorphic graphs have same distance spectrum, then these graphs are called distance co-spectral graphs. A graph is determined by its spectrum means that there exists no non-isomorphic graph with the same spectrum as that of G. Then we can say that G is determined by its spectrum. The hyper D cube is determined by the spectrum of its distance matrix. This is proved by Coulon in 2016. But in the case of adjacency spectrum, this is 4 cube when D equal to 4. 4 cube is this graph and this is the Hoffman graph. And it is easy to prove that these two graphs are non-isomorphic. But these two graphs have the same adjacency spectrum. But we have already said that hyper D cube is determined by its distance spectrum. So, D cube is not determined by its adjacency spectrum, but it is determined by its distance spectrum. Now we come to the definition of distance energy. Distance energy is defined by Dr. Indulal and Vijay Kumar in 2008. In any matrix, the energy, any square matrix of real entries, the energy is defined to be the sum of absolute values of eigenvalues. In the case of distance matrices, the distance energy is defined as the sum of the absolute value of the distance eigenvalues. And distance energy finds applications in chemistry. And the relation is that the graph energy is related to the pi electron energy according to the Huckel molecular orbital theory. And the molecular orbital energy levels can be identified with the graph eigenvalues. In the case of distance matrix, it finds applications in the design of communication networks, network flow algorithms, graph embedding theory, as well as molecular stability. Bellabene, Ciubertiu, Mendelino used it as a molecular descriptor and used in qualitative structure property relationship modeling, and was successfully used to infer the extent of branching and model boiling points of alkanes. We have the diagonal entries of the distance matrix as zeros. That means the trace of the distance matrix is 0. That is, the sum of the eigenvalues of the distance matrix is 0. So, the sum of the positive eigenvalues cancels with the sum of the negative eigenvalues. That is, sum of the positive eigenvalues is exactly equal to minus of sum of the negative eigenvalues. We know that energy is the sum of absolute values of all the eigenvalues. So we can say that energy of a graph T is twice the sum of the positive eigenvalues. Or similarly, we can say that energy of a graph is minus 2 times the sum of the negative eigenvalues. Thus, we get the distance energy of G equal to twice summation lambda I greater than 0 lambda I, which is same as minus 2 times summation over lambda I less than 0 lambda I. We need not consider the 0 eigenvalues because it will not contribute to the sum. So, if we consider a graph with a unique positive eigenvalue, distance eigenvalue, then the sum of the positive distance eigenvalue will be exactly that unique positive distance eigenvalue. So, to find the distance spectrum, we only need to twice that unique positive distance eigenvalue. So, the distance energy of a graph with unique positive eigenvalue will be twice its unique positive distance eigenvalue. That's the importance of graphs with unique positive distance eigenvalue to the distance energy of graphs. These are some examples of distance energy of graphs. Pn denotes a path of order n. There is no closed formula for the distance energy of a path. This is an approximate formula for finding the distance energy of a path. That is 0.6948 n square minus 0.7964. And this is the distance energy of a cycle. It is n square minus 1 by 2 when n is odd and is n square by 2 if n is even. We have seen that all the trees are having unique positive eigenvalue. So the path also have a unique positive eigenvalue. Similarly, Bipartite proved that unicyclic graphs have a unique positive distance eigenvalue. Therefore, Cn also have a unique positive distance eigenvalue. So if we consider Cn, we can see that we have already seen that it is transmission regular. So sum of the entries of each row is a constant. So that constant is exactly n square minus 1 by 4 if n is odd and n square by 4 if n is even. So the unique positive eigenvalue of Cn is n square minus 1 by 4 in the case of n is odd and is n square by 4 if n is even. So the distance energy is twice of that spectral radius. Also star, we consider star Sn. This is star on n vertices. It is also a tree and have a unique positive eigenvalue. Therefore, this is twice the spectral radius. The distance energy of star is twice the spectral radius. The spectral radius is n minus 2 plus root of n minus 2 whole square plus n minus 1, and twice of the spectral radius is the distance energy of the star. Now we consider complete bipartite graph KMN. It is known that the distance energy of complete bipartite graph is 4 into m plus n minus 2. Complete bipartite graph is having two positive distance eigenvalues. The distance energy of a complete split graph CSMN is given by 2 times 2m plus n minus 3. We can have many problems related to distance matrices and distance spectrum, distance spectral radius, distance energy. We can have energy bounds, bounds for spectral radius. That bounds can have parameters like order of the graph, that means number of vertices, size of the graph, that is number of edges, decrease of the vertices of the graph, like that. So we can find bounds for the distance energy, distance spectral radius, like that. We can characterize graphs among a specific family or class of graphs with extremal energy. That is, we can find the possible class of graphs with maximum energy and in a class of graphs with minimum energy. In the case of trees, the graphs, trees having maximum energy is path, and among the trees, the graphs having minimum energy is star. So in a class of graphs, we can find which graphs have minimum or maximum energy or spectral radius. We can consider bipartite graphs, we can consider unicyclic graphs, like that. We can find how the distance energy changes on vertex deletion or on edge deletion or types of subdivision of graphs. By deleting vertices, we will get induced subgraphs. By considering edge deletion, we can consider any edge we can delete or some particular edge we can delete, and we can have problems like that. So these are some types of possible problems in the case of distance matrices. And we can use different methods to solve these problems. One is the method of having equitable partitions. The equitable partition I am going to define. Let A be a real symmetric matrix that is partitioned into blocks, where A equal to A11, A12, A1R, etc. Then we can have integers Qij as the average row sum of Aij, and we can form a matrix with the entries as Qij and call that matrix as Q, the quotient matrix of A. Qij is the average row sum of Aij, and Q is the quotient matrix with entries, ijth entry as Qij. Sometimes the row sum may be a constant. In that case, the average row sum will be that constant row sum of that block. In such cases, we call that partition as equitable partition. If the row sum of each block of the block Aij is a constant, then the partition is called equitable. If for all the blocks it is different constants, then we call this partition as equitable partition. Now, what is the advantage of having an equitable partition or a quotient matrix? Let Q be a quotient matrix of a square matrix A. corresponding to a partition of A. Then the eigenvalues of Q interlace the eigenvalues of A. That is the result. If Q is the quotient matrix, then the eigenvalues of A Q interlace the eigenvalues of A. If we consider the partition as equitable, if we get an equitable partition, then the spectrum of the matrix A contains the spectrum of Q. This is A, sorry. The spectrum of A contains the spectrum of Q. That is, all the eigenvalues of Q will occur as eigenvalues of A. And the spectral radius of A and Q will be the same. If the partition is equitable, the spectral radius of A is same. This is the advantage of equitable partition and form the quotient matrix. Now, another important result is Cauchy's interlacing theorem for symmetric matrices. If A and B are two symmetric matrices, A is a matrix of order n and B is a matrix of order m, and A have eigenvalues alpha 1, alpha 2, etc. alpha n, and B has eigenvalues beta 1, beta 2, etc. beta m. The spectral radius of A is alpha 1 and the spectral radius of B is beta 1. Then, if B is a principal submatrix of A, then alpha k greater than or equal to beta k greater than or equal to alpha k plus n minus 1. This is the interlacing of eigenvalues. In particular, if m equal to n minus 1, then we can have this result as alpha 1 greater than or equal to beta 1 greater than or equal to alpha 2 greater than or equal to beta 2 greater than or equal to etc. beta n minus 1 greater than or equal to alpha n. This is more interesting. Consider H as H is connected graph and having an induced subgraph, connected induced subgraph G of order m. Then if you consider the adjacency matrix, then the adjacency matrix of H will be a principal submatrix of the adjacency matrix of G, because if we consider induced subgraph, if Vi and Vj are adjacent in G, and if Vi and Vj occur as vertices in H, then if Vi and Vj are adjacent in G, then Vi and Vj will be adjacent in H. So the ijth entry will be the same in the adjacency matrix of G and H. And if Vi and Vj are non-adjacent in G, then they will be non-adjacent in H. So the adjacency matrix of H will be a principal submatrix of the adjacency matrix of G. Therefore, by interlacing theorem, the adjacency eigenvalues of H interlace the adjacency eigenvalues of G. This will not be true in general for the distance spectrum. This is a graph, this is C5, and we consider the U1, U4, the entry U1, U4. U1 and U4 are at distance 2. So the 1/4 entry is 2. If we delete an edge, a vertex, delete a vertex U5, then the distance between U1 and U4 will be 3. Distance between U1 and U4 will be 3. Then the 1/4 entry changed. Before it was 2, 1/4 entry, now it is 3. So in the case of induced subgraphs, the distance matrix of the subgraph need not be a principal submatrix of the original graph's distance matrix. So the interlacing need not be true for the case of distance spectrum of induced subgraph. Many researchers have considered distance matrix, distance eigenvalue, distance energy. Recently, after probably in 2000, after 2000, we discuss mainly the change of distance energy when an edge is deleted. How the distance energy change when an edge is deleted. We have seen that when an edge is deleted, the entry increase because the distance will increase. In the case of adjacency matrices, if an edge is deleted, if VA and VJ are adjacent in G, if the edge is deleted, then VA and VJ will not be adjacent in H. Then the ijth entry changed from 1 to 0. The ijth entry was 1 when they are adjacent, and the ijth entry will be 0 when the edge is deleted. So entry wise the matrix becomes smaller. There is a result that if A is greater than or equal to B entry wise, then the spectral radius of matrix A is greater than or equal to spectral radius of B. In the case of adjacency matrix, since the adjacency matrix of G is greater than or equal to the adjacency matrix of H entry wise, the adjacency spectral radius of A will be greater than or equal to adjacency spectral radius of H. I mean, the adjacency spectral radius of G is greater than or equal to adjacency spectral radius of H in the case of adjacency matrices. But in the case of distance matrices, when an edge is deleted, entry wise the submatrix corresponding to the subgraph distance matrix will increase entry wise. So that distance spectral radius also increase. Also, we can't use interlacing theorem. So we can't use it for finding distance energy in general. So we have to investigate how distance energy changes when an edge is deleted. In the case of adjacency matrices, how the adjacency energy changes. This problem was studied by Jane Day and Wasen So. Motivated by this, we have studied the energy change, distance energy change of graphs when an edge is deleted. Day and So proved that when a bridge is deleted, that is the new graph is G minus E, then the energy of G minus E is less than energy of G. Since all the edges of a tree are bridges, if we consider a tree, then if any edge is deleted, then energy of G minus E is less than energy of G, if G is a tree. If G dash is an induced subgraph, they proved that the energy of G dash is less than or equal to energy of G. And the equality holds if and only if G dash and G has the same edge set. That means if we remove only isolated vertices, then the edge set will be the same. Then such induced subgraphs will have the same energy. Energy will not change. And also they found infinite classes of graphs with the property that deleting an edge increase the energy. Also, they found existence of infinite families of graphs whose deletion causes decrease of energy, and infinite classes of graphs having no energy change on edge deletion. But in the case of distance matrices, on almost all the trials, we found that graphs are having distance energy increase while removing an edge. We thought that it may be common or for all the graphs this may be true. But later we found a counterexample. That is, there exist graphs such that on deletion of an edge, distance energy decreases. So, also one more problem in the case of distance matrix is that we could consider only connected graphs. Otherwise, in different components, the vertices, the distance will be infinite and we can't manage the distance matrices. So, we should consider the edge deletion provided after edge deletion, the graph should be connected. If a graph is having a unique positive eigenvalue, we know that the distance spectral radius increase on edge deletion. So, the distance energy is twice the distance spectral radius. So, clearly, the distance energy will increase for the graphs with unique positive eigenvalue. If we consider complete graphs of order n, if we delete an edge, it is also a graph with unique positive eigenvalue. So we will get the distance energy of Kn is less than distance energy of Kn minus E. Kn minus E denote the edge deleted subgroup. In the case of Cn, Cn is also a graph with unique positive distance eigenvalue. Distance energy of Cn and distance energy of Cn minus E. We know that if we delete an edge, we will get the path on n vertices. And it is also a graph with unique positive distance eigenvalue. So, the distance spectral radius of Cn is less than the distance spectral radius of Pn. So, twice the distance spectral radius of Cn is less than twice the distance spectral radius of Pn. So, distance energy of Cn is less than distance energy of Pn. And if we compare how the distance energy increase on edge deletion, we know that complete graph have all the vertices are adjacent each other. If we delete an edge, entry wise the increase of the entry is comparably less. If we compare the edge deletion of a Cn, then we will get Pn. That is, if we consider a cycle of 100 vertices, then if we delete an edge, the two vertices which were at distance 1 will be changed to a pair of vertices with distance almost half, that is 50. The distance between these two vertices will be 50. So, sorry, not 50, it is 100. So, if we the deletion of the edge affects different graphs differently. So, in both graphs, edge deletion increases distance energy, but that increase is different. In the case of complete graphs, if we delete an edge, as n tends to infinity, we can find the difference of distance energies because we can have explicit formula for Kn minus E and its distance energy. So we can find this formula ed of kn minus e minus ed of kn. And as n tends to infinity, we can see that this difference tends to 0. But in the case of Pn and Cn, this difference tends to infinity. That's a very wide variation. And we have considered unique positive eigenvalue graphs. And we have compared the distance energy on edge deletion. And naturally, some questions arise. It's the property of having unique positive eigenvalue, a necessary condition for the increase of distance energy by deleting an edge, or whether there exists graphs with more than one positive eigenvalue and having distance energy increased on edge deletion. Second question is that, does the deletion of an edge always increase the distance energy of any graph? Or does there exist graphs such that on edge deletion, the distance energy will decrease? For many examples, we have found increase of distance energy. We prove that complete bipartite graph. It's a graph having two positive distance eigenvalues. So the first question is solved. We found that the distance energy increases on edge deletion. And we can have a set of examples of connected graphs in which distance energy decreases when a specific edge is deleted. So such examples also exist. That answers the second question. We considered complete bipartite graphs. If m and n are greater than or equal to 2, surely on edge deletion kmn minus e will be connected. And we have the distance energy of kmn, already known result. It is 4 into m plus n minus 2. And kmn is having minus 2 with multiplicity m plus n minus 2. And for kmn minus e, it is difficult to form an exact formula for distance energy. But we compared the distance energies of kmn and kmn minus e. For complete bipartite graph, the distance eigenvalues of kmn minus e are minus 2 with multiplicity m plus n minus 4 and 4 other roots which are unknown, and these roots are exactly the solutions of this polynomial p of x. And using this, we compared the distance energy of kmn and kmn minus e and found that the distance energy of kmn is less than the distance energy of kmn minus e. Also, we had a conjecture. The distance energy of k, n1, n2, etc. nr is less than distance energy of k, n1, n2, etc. nr minus e. The distance energy of k, n1, n2, etc. nr is already known to be 4 into n1 plus etc. nr minus r. But distance energy of k, n1, n2, etc. nr minus e is not known. And the conjecture is partially proved by Tian et al. And they proved that the distance energy increases on edge deletion for complete multipartite graphs with n1 equal to n2 equal to etc. nr. And also they proved that the distance energy increases on edge deletion for Turan graphs. This is an example. An example, we found that it is infinite but not proved that this is a graph with n vertices. This is a graph with 11 vertices, and this is a graph with 12 vertices. When we delete an edge from this graph, we will get this graph, and by using MATLAB we have found that the distance energy decreases on edge deletion. So this is an example for a graph whose deletion causes decrease of distance energy. And for many trials on extension of adding pendant edges like this, we have found that this decrease causes. So we feel that this is an infinite family of graphs whose edge deletion decreases distance energy. These are some books on graph spectra. This is a book by Xiang Li, Shi, and Ivan Gutman on graph energy. This is a book on graph spectra. This is a book for graph theory by Dr. Balakrishnan Ranganathan. And this is a book on spectra of graphs. And this introduction to the theory of graph spectra by Chekhov, Rawlinson, and Simic. And some parts of these results are published in Linear Algebra and Applications in 2018. These are the references. Thank you.
Yeah, thank you, Dr. Anu, for the interesting talk. Yeah, audience, if you have any question, you can ask.
Hello, ma'am. Can you go to
Yeah.
the slide number 32?
32.
Yes. So, ma'am, you are saying कि if we are deleting edges, so it will decrease the distance energy.
This is the distance energy for some graphs. That infinite example.
Okay. So, ma'am, so means we can also say that if we add a edge to a graph, provided
And an edge.
its order is same, then the distance energy will increase.
That is the reverse process of edge deletion. Did you mean
Can we
that?
say that?
But both cases will occur. On edge deletion, sometimes for some graphs, distance energy may increase.
Exactly. So means,
Okay. Uh,
ma'am, I'm saying that if we are adding the
Adding an edge, we can have an energy increase or energy decrease according to that graph. For some graphs, energy will increase. For some graphs, energy will decrease. I have shown an example.
okay,
Last example. In that example, if we
okay,
add
thank you.
a pendant edge, then the energy will increase. The other case, in the case of C, the energy on edge deletion, the energy will decrease. Not edge deletion, on edge addition.
Okay, it is
Is it clear for you?
okay.
Yes.
subset if suppose H is a given graph, if H is a graph obtained by deleting a vertex, then the adjacency matrix of H is the principal submatrix of adjacency matrix of G.
Ah,
Right, but this result may not be true for distance.
one deletion of vertex.
You have, yes, ma'am.
And
You have
deletion of
given an
vertex.
example. Yes.
Ah, yes.
Ma'am, under what condition, is there any result, under what condition would imply the result would be true? Or otherwise, does there exist a class of graphs for which the distance matrix of H would be a principal submatrix of distance matrix of G? Is there any other result?
Yes,
This is true for distance hereditary graph.
ma'am. Yes.
This is true for distance hereditary graphs.
Okay.
It preserves distance if we consider induced subgraphs. Okay. Is it clear for you?
Yes, ma'am. Thank you.
Okay.
Yeah. Any other questions? Okay, Dr. Anu, I have two questions. I think one is possibly a typo in your slide. The determinant formula for distance matrix. The determinant formula for distance matrix.
Formula for distance matrix of
tree. Mr.
This is just an formula for which one?
Distance matrix of trees. Tree.
These trees. Determinant. Did you mean determinant?
I think the formula should be minus 1 power n minus 1 into 2 power n minus 2. Just a minute. Dr. Suresh, can you mute your mic? Suresh M. Yeah, I think now it will be clear. Yeah, formula for the inverse of tree. Yeah, not inverse, sorry, determinant.
This is taken by Bipartite.
It's
I don't know whether there's any typo.
Okay. So in Bipartite book I read there. I think the result says that yeah, minus 1 power n minus 1 into n minus 1 into 2 power n minus 2. Yeah, that is one thing.
Okay, maybe a typo.
That's a typo. Yeah, possibly a typo. And one more. Oh, I think there is some network issue. Yeah, maybe let's wait for 1 minute. Okay. Yeah. Dr. Anu?
Yes, sorry, I lost connection for a while.
No problem. Yeah, actually, your conjecture, whatever that energy of distance energy of k n1 n2 nk is strictly less than energy of k n1 n2 nk minus e.
Yes.
That conjecture is recently proved. Recently means just 5 days back.
Yes.
Yeah, you know. Yeah. Professor, I think Showai's son and Kinkar Chandra Das, they have proved.
Yes.
Yeah.
That's.
Yeah, these are the 2 points I want to make. Yeah.
Yes, I have seen.
Yeah. Okay. Okay. Audience, you have any other questions? Okay, if not, let us thank Dr. Anu for her interesting talk. Dr. Anu, I have recorded the talk. I will put it in YouTube, and then, if possible, please send the slides. I will circulate to the participants.
Okay, okay, I will send.
Yeah,
Thank you.
thank you so
Thank
much.
you for your Thank you. Thank you all for kind attention.